In this video, we're going to walk through an overview of our material we've covered about solution chemistry. So I'll start right off the bat with some definitions. So thinking about what a solution is, it's going to be comprised of a solute and a solvent. The solvent is whichever of the two things you're combining you have the most of. And when we combine these together, we get a solution. Now, a solution is going to, we've already kind of defined this before. It's also a homogeneous solution or a homogeneous mixture. And so when we talked about matter at the very beginning of our class, we said you could have these heterogeneous mixtures and homogeneous mixtures. And a homogeneous mixture would look uniform. It would look like it was one thing. Whereas a heterogeneous mixture, you'd be able to see two different phases, or you'd be able to see different colors. It would look like two things combined. And so these are all going to be uniform. They're going to have the solute completely dissolved in the solvent. And that word dissolved means that it is each molecule or atom of our solute is surrounded by solvent particles. So let's say we've got, I'm just going to draw a thing. So we're going to have these little water molecules, and we're going to show them as being around a solute particle. And that's what we think of when we think of something being dissolved. Okay. So the other kind of way that we think about these solutions now that we have talked about intermolecular forces is through that lens, which is to say that we know if a solution is likely to form if we can compare the intermolecular forces that the solute and the solvent have and see that they're similar. And we've got kind of a shorthand rule for this. It's called like dissolves like. And this means that when you have similar intermolecular forces, your solutions can dissolve, or your two components or compounds can actually dissolve in one another. And so this means that we're going to see polar compounds dissolve in polar solvents. And our nonpolar compounds will dissolve in nonpolar compounds. And within that, we'll see that with our polar compounds, it's not just things that are polar, but also things that are charged. So we'll put a little asterisk there. And so we can track these solutions and how much we have of our solute and how much we have of our solvent by describing that ratio. And that's what we think of as concentration. So it's really communicating what the solute to solvent ratio is. And this can be different every single time you make a solution. It's not a physical property that's inherent to a solution. I mean, it has a concentration, but that concentration can change, and it depends on how it's made. And so there's lots of ways to track concentration and ways to communicate, here's how much solute I have and how much solvent I have. And the ones that I think are the most important to learn that we use in our daily lives and that we use in medicine and that we use in the chemistry lab are molarity. This is the chemistry lab one, which is really equal to the number of moles we have over volume in liters of the solution. And then we use percent mass per volume a lot as well, which is really equal to the mass of our solute divided by the volume of our solution in milliliters. Times 100. So those two we use a lot. We also use volume per volume, percent volume per volume as well, which is really similar to our mass per volume, except you're taking the volume of the solute rather than the mass. And then another one that's common if we're talking about something that we have a very small amount of solute for is parts per million or parts per billion. And so you see a lot of this when we describe things like tracking toxins or contaminants in water supplies, things like that. So we have parts per million, which we abbreviate ppm, and parts per billion. And for these ones, it's really the same thing as a mass per volume or a volume per volume calculation, except it's instead of times 100, it's times 10 to the 6. So it might be something like volume of our solute divided by the volume of our solution times 10 to the 6. That would give us parts per million. And of these, the ones that I think are the most important to know very well leaving this class is molarity, percent mass per volume, and percent volume per by volume. And so I'd like everyone to be comfortable with how to use those. And so that's how we'll communicate and track concentration. But we also kind of cover how to manipulate that as well. And so we use this equation for dilution. So we can determine what concentration we have if extra water is added to it. And it's C1V1 equals C2V2, where that C is corresponding to concentration, and that V is volume. You might also see this as M1V1 equals M2V2, where that M is molarity, which is a type of concentration. And really what we're doing here is whenever we have concentration times volume, it equals moles. And so we can set the moles of our solution before we add water equal to the moles of our solution after, because we haven't actually changed the amount of our solute. We've just changed the total volume of our solution, and that's it. And so the number of moles will be the same. And so as we add more water or solvent to a solution, that concentration will decrease. So concentration will go down as our volume goes up, and our moles of our solute stay the same. Our colligative properties then are about the concentration of solute particles that we have in our solution. And so our concentration can tell us a lot about how a solution will behave, its physical properties. And those are going to be our colligative properties. And the interesting thing about these is they have nothing to do with the chemical identity of the solute or the solvent. It just has to do with the number of particles that are occupying space within the solution and separating solvent particles from each other. And so this is independent of chemical identity. And there's a number of these that we can track, but there's one we focused on the most, and that is osmosis or osmotic pressure. The other ones that we talk about is freezing point depression. This is when you lower the freezing point of a substance as you increase the concentration of the solute, and boiling point elevation. And this is when we see the boiling point of a solvent increase as we increase the concentration of solute particles within it. And then within osmosis, we're really talking about osmotic pressure, which we won't go through the calculation for. It's kind of similar, though, to calculating pressure for a gas. But instead, we're going to look at this comparatively and looking at things on two sides of a semipermeable membrane. So here, semipermeable. So if we have a semipermeable membrane, we have something that water can cross, but our solute particles cannot. And if we have two solutions separated by a semipermeable membrane and they're the same concentration, then the water will pass going in both directions and nothing will really change. But if we have something with a higher concentration and an area with a lower concentration, we'll see that water moves across the semipermeable membrane to try to equal out the concentrations, which means it'll try to dilute the higher concentration. And so water will cross the semipermeable membrane and dilute the higher concentration side and increase the volume of it. So water, this I got from a student and I love it. It's water always follows the party. And so water is always going to travel across a membrane to the side with the higher concentration. Now the trick with these is evaluating which is the higher or lower concentration, because colligative properties depend on the number of solute particles in solution, and that's really going to be about the number of these particles, like we drew up here, that are surrounded by solvent molecules. And if I have an ionic compound, like let's say sodium chloride, when it dissolves in solution, it breaks apart into its positive and negative ions, and it's completely surrounded by water molecules. And so in this case, I have 2 particles for every 1 mole of my sodium chloride. And so if I have a concentration that is, let's say, 0.1 molar NaCl, I'll actually have a 0.2, so I multiplied it by 2, molar concentration of particles in solution. And so that's the value I would use to evaluate what my concentration was in terms of osmosis, to see if water would leave that side of the semipermeable membrane or if water would come into it. So that's a one to be careful of. Also within osmosis, we've talked about this in the context of the human cell and how this translates into the terminology isotonic, hypotonic, and hypertonic. So if we have 2 solutions on either side of the cell membrane, so we'll go like this. So we have a cell membrane. So if our concentrations are the same on either side, get rid of this arrow, then we have an isotonic solution. And if one side is higher, and let's make one of these a cell. Here we go. So if we have a higher concentration on the outside of the cell, then we're going to have a hypertonic solution around the cell. And if we have a higher concentration inside the cell and a lower concentration outside of the cell, then we're going to have a hypotonic. And so when we have a hypotonic solution, we're going to see water go into the cell and the cell will expand. And if we put that cell in a hypertonic solution where it's a higher concentration outside of it, then water will travel outside of the cell from inside to try to dilute that higher concentration. And we'll see the cell shrivel up. And it won't change if it's the same.